Okay. So we have started seeing some undecidability proofs. So I will continue with this today. And tomorrow we will see a very surprising result that undecidability is in a sense the rule. Okay. So it's a very powerful theorem called Rice's theorem. Anyway, so let us look at a second example. This is also very important. Of course, this follows from Rice's theorem, but let us have a self-sufficient proof. So you are given a Turing machine M, or in other words, actually the encoding of M, and you are supposed to decide whether its language is regular. Even this problem cannot be decided. In fact, we will later see this problem cannot even be semi-decided. Okay. Anyway, we will see that later. But for the moment, as a second example of reduction, let me prove this statement. Okay. So, as is a very conventional way of doing this undecidability proofs, we use reduction from HP. For that matter, we may start from any other language which is proved to be undecidable, but following this Cozen kind of stuff, Cozen kind of style, I would say, we will make reduction from HP, the halting problem. Okay, so the output will be a single machine N. Okay, and the input is an instance of the halting problem, that is a pair of encodings M followed by W. Hash is the separator as usual, and this N will have in its head, first of all, M and W, information about this M and W. In this example, N also stores the description of some other machine U. Later we will take U to be the universal Turing machine. But for the moment, it maybe it's not needed to be the universal Turing machine, but it's only needed that the language of U should be non-regular. That's all we need. Okay. But the same example will prove many things. So for that, we will eventually take U to be the universal Turing machine. So it's a fixed Turing machine. And whenever I say that N has in its head information about these two Turing machines, M and W, I essentially mean that all the transitions of M are there in the finite control of N. Likewise, all the transitions of U are there in the finite control of N. And at suitable time, maybe after doing some bookkeeping or other stuff, the finite control switches to the start state of M or the start state of U. And of course, I re-encode M and U if necessary in such a way that they do not share any state. So that whenever this machine switches to the start state of M, for example, it will keep on simulating M. Okay. Until M reaches some conclusion, T or R. From that, we will make some transition to some state if there are some other pending task. Okay. This is how this thing goes. So henceforth, I will not very specifically tell what the states of N are and all that stuff. Instead, I will just mention the behavior of n on its own input. Okay. Okay, so let's see the behavior of n. Okay, so this is a reduction, and the input is an instance for the halting problem, m and w. Output is a Turing machine whose language is regular. It should be. Actually, this reduction will prove just the opposite, but anyway, I will later come to the conclusion that this does not really matter because recursive languages are closed under complementation. So a Turing machine whose language should be regular if and only if m halts on w, but the reduction that I am going to show will actually establish a Turing machine n whose language is not regular if and only if m halts on w. So that basically says the complement of this language is not recursive, but recursive languages are closed under complementation. Therefore, the original theorem actually follows. Anyway, so let us see. So n has the information of m and w embedded in its finite control in the form of this transition diagram. And n also embeds the information of another fixed Turing machine, u, in its finite control. Later, we will take u to be the universal Turing machine. Okay. And take any language L that is recursively enumerable, but not recursive. Okay. So take any Turing machine U whose language is L. For example, I can take L equal to MP. In that case, U will be the universal Turing machine. Or I can take L equal to HP itself, in which case U is a universal Turing machine prime, U prime. Okay, whatever. It's a fixed machine. So its transition diagram can be embedded in the head of, in the finite control of the target machine N. Okay, so I only specify the behavior of N on its private input V. So it does this. So this is the initial part, some kind of bookkeeping. After that, it will go to M. It will switch to the start state of M. So store V on a separate tape or track. So N has its private input V, which has nothing to do with W. Okay. Then it, for the moment, it stores it for processing afterward. So then what it will do, it has the information of W in its finite control. So it will write W on its tape and simulate M on W by simply moving to the start state of M. Okay. Then if the simulation halts, okay, if the simulation halts, if that simulation never halts, then this machine never comes out of the second step or second stage, okay, or phase. Then it will copy back V from the second tape or track to the first tape or track and simulate U on V. Okay. So this is the initial bookkeeping stage. This is also part of that, write W on the tape and simulate M on W basically means switch to the start state of M and then it does exactly what M does. Okay. And when the simulation halts, there is some other thing to do. So it once again copies V back to the first step or track and then switches to the start state of U. So from that onward, it is basically the simulation of U on V. Okay. And if U ever accepts, N also accepts. If U explicitly rejects, U also explicitly rejects. And if U keeps on looping, the simulation will never stop. Simulation of this stage. Okay. So now let us see what is the language accepted by N. So for n to accept, first thing, this simulation must stop. In addition to that, you should accept V. Okay. So n accepts if and only if both the following conditions hold. First, M halts on W, and second, U accepts V. Of course, acceptance is only by halting, so that's not important. So U accepts V. Therefore, okay, I have this, the language of M is equal to the language of U if M halts on W, and if M does not halt on W, then this simulation never ends, and this machine N has no chance to come here and simulate U on V. So it accepts nothing. Okay. Now, this phi is a regular language, whereas L, if it is MP, okay, and if U is the universal Turing machine, this language is recursively enumerable but not recursive. In particular, it is also not regular. It is not context free. It is not context sensitive. Nothing. Okay. Therefore, yeah, so phi is regular. Oh, I should write L here, right? It is not A. L is not regular. Okay, so that's a typo. Anyway, I'll correct it. And what is this? Let L2 be the okay. This is the language, a set of all n such that L of n is regular. Then actually we have made a reduction from the halting problem to the complement of L2. But as I mentioned, for undecidability proofs, this is perfectly fine. The reason is that this actually proves L2 complement is not recursive rather than L2. But if L2 is recursive, its complement will also have to be recursive because recursive languages are closed under complement. Okay. So for undecidability proofs, this is just fine. You may propose a reduction to the language of concern or its complement. Doesn't matter. Okay. Recursive languages are closed under complementation, so L2 is also not recursive. And there is some alternative argument. You can go through it. It's not really that important. Okay, for undecidability proof, it's sufficient that you can propose a reduction from HP or something to the language in concern or its complement. Okay. And now, of course, if I take that U to be the universal Turing machine, so that this language L is recursively enumerable but not recursive, then it is, as I mentioned, it is not finite, it is not regular, it is not context free, it is not context sensitive, it is not recursive. Therefore, this reduction proves all this host of results. The problem whether the language of a Turing machine is finite is undecidable. Okay. Context free, context sensitive, or recursive. Okay. The problem whether the language of a given Turing machine is recursive is undecidable, whereas this is trivially true. The problem whether the language of a given Turing machine name is recursively enumerable, this is trivially decidable. This is always true. Okay, irrespective of whether the machine is a total Turing machine or not, its language is recursively enumerable, which is by definition of recursively enumerable languages. Okay. So this last point is basically what is called a trivial property that I will discuss tomorrow. Okay. But we have been able to prove the first four and also regular thing. Okay, we cannot decide this. So in general, all these proofs are based upon, let's say, two important theorems. If there is a reduction from a language A to a language B, and if B is recursively enumerable, then also A is recursively enumerable. Okay. So we will not usually use this theorem in this fashion. Indeed, we will use the contraposition. If A is not recursively enumerable, then B is not recursively enumerable. Okay. So this is how we will typically use. Okay. And the proof is fairly straightforward. Suppose that sigma is a reduction from the problem A to the problem B. Then I want to solve A. Okay. Sorry, I want to solve A. So I will use this reduction map and convert an instance for A to an instance for B. And since B is assumed to be recursively enumerable, it has a Turing machine. Let us call it N. Okay. So a recognizer for A can be designed as follows. On input A, W, M first applies sigma to generate sigma W from W. So that is an instance for B. And because this is a reduction map, it is computable in a finite amount of time. It is doable by a total Turing machine. Okay. In addition, the reduction property says that W is in the language of M, that is in A, then sigma W will be in B, and if W is not in A, then sigma W will not in B. Therefore, if this machine N or M runs this Turing machine N on this converted instance sigma W, then it can simply forward its decision. If N says yes, M will say yes. If M says no, N says no. If M loops, N will also loop. Okay. So run N on sigma of W, the converted instance, and just follow whatever N does. Accept, accept, reject, reject, loop, loop. Okay. Okay. So that's the proof of this. But as I mentioned, I will usually use this theorem in the contrapositive way. If A is not recursively enumerable, then B is also not recursively enumerable. And this is the same theorem about recursive languages. Okay. So if there is a map from A to B, and if B is recursive, then A is also recursive. Contrapositively, if A is not recursive, then B is also not recursive. And we have already seen several reduction examples based upon that contrapositive idea. Right. So what is the proof? The proof is exactly very similar. Let B be recursive, and sigma is a reduction map. Then by the previous theorem, if B is recursively enumerable, A is also recursively enumerable. Okay. Also, you note that sigma is also a reduction map from the complement of A to the complement of B. Okay. Therefore, once again by the previous theorem, since B is recursive, right? Therefore, its complement is recursive and therefore recursively enumerable too. So once again, I can see B complement is recursive and therefore recursively enumerable. And I have a reduction from A complement to B complement. Then again by the previous theorem, A complement is recursively enumerable. Okay. So what I do have now, A is recursively enumerable, A complement is recursively enumerable, therefore A has to be recursive. Okay. So this theorem you have seen, right? If both a language and its complement are recursively enumerable, then that language has to be recursive. Hmm? Oh, you have not seen this result? Okay, if not, this is a simple proof for this. A is RE. So A has some Turing machine. Let us call it T. Total. No, it need not be total. A complement is also RE. Therefore, it has a Turing machine, T complement, T prime, whatever you call it. So, for all inputs in A, T halts after accepting. And for all inputs not in A, T complement halts after accepting that input. So if these two simulations run in parallel in time sharing fashion, then either T will halt or T complement will halt, depending upon whether it is in the language A or not. So these two together, if you run in parallel, this gives you a total Turing machine for A or A complement, whatever. Okay, so that's the proof. Yeah. Okay. So now, with this very intuitive but powerful theorems in our hand, we have these three situations. It is possible that some language and its complement are both recursive. It is also possible to have non-recursive but recursively enumerable language like HP. Okay. So this is demonstrated by the language B. But if B complement is recursively enumerable, then B is recursively enumerable, B complement is recursively enumerable, and therefore B will have to go in this inner circle. Since that is not the case, so B complement has to be outside this RE box. Okay, so this is the second type of thing. This is a thing for which you have many, many examples. And this is a thing for which you have a few examples like the halting problem, membership problem. Okay. It is also possible that there are languages for which both that language and its complement are not recursively enumerable. Okay. So this is demonstrated by this. So these are three possibilities. Okay. So both A and A complement and RE, and therefore both are recursive. So B is recursively enumerable but not recursive, and therefore B complement has to be non-RE. And these are examples that we have seen. And the third possibility is both C and C complement are non-recursively enumerable. Okay. So what I will do in the rest of today's class, I hope I have enough time. Yes. I will look at an example of the third type. Both a language and its complement are non-RE. Okay. So, yes. So, these two deductions I am going to cover now, and carefully listen to this because these are very, I would say, prototypical. This kind of reductions apply to many problems, many problems, I would say. So this is some I would say, kind of whenever you solve integration by parts, it's a kind of generic procedure. Okay, and the two deductions that I am going to introduce, these are also something like this generic. Okay, they apply to a lot of problems. Okay, so to demonstrate this third possibility, I will prove neither this language finite, affine or finite, as that set of all M such that the language of M is finite, nor its complement is recursively enumerable. So what is the complement of this language? A set of all encodings of machines whose languages are infinite. Okay. And actually we have proved that fin is not recursive. This is our deduction example 2, right? We have proved that fin is not recursive. Now I will prove a more, I would say, powerful statement. Fin is not even recursively enumerable. Okay. So let us see. So I will have two proofs. First, I will show that fin is not RE. Then I will show by a separate reduction that the fin complement is not RE. Okay. Same reduction will not hold in this case. Okay. Because if some language is not RE, its complement may be RE. So I need two proofs. Only one proof will not suffice. Okay. Okay. Actually, we have proved fin is not recursive by reduction from HP, but this does not establish that fin is not RE. So if you want to apply this theorem, and I need a reduction from a non-RE language, not a non-recursive language. And what language we have in our hand? HP complement or NP complement. So these are non-RE languages. HP is RE, MP is RE, although not recursive. So by reduction from HP or MP, you will not prove anything except undecidability. It will not prove unsemi-decidability. Okay. So we need to have a reduction from a non-RE language. And following Poisson's conventions, we will take HP complement. Okay. So HP complement is a set of all M W pairs. Such M does not halt on W, and we know this is non-RE. So I will supply a reduction, two reductions actually. First, I will reduce the problem of HP complement to fin and also HP complement to the complement of fin. And reductions are actually in some sense closed under complementation. So the first reduction is actually a reduction from HP to fin complement. And the second reduction is actually a reduction from HP to fin. You may view it this way, but in order to understand things better, let us talk this way. It's a reduction from the complement of HP to fin that will establish fin is not RE. I will have a second reduction from the complement of HP to the complement of fin that will prove the complement of fin is not RE. Okay. Okay. So, as I told, these are going to be very prototypical reductions. So the first reduction, I will reduce the complement of HP to fin. So the input is a pair of encodings M and W. M is the encoding of a Turing machine and W is the encoding of an input for M. And the output will be some Turing machine M. And because this is a reduction, we must have that the language of N is finite if and only if M does not halt on W. Okay, so far we are using L of N is something if and only if M halts on W, but since now the reduction is from the complement of HP, okay, the reduction now should satisfy this. The language of N will be finite if and only if M does not halt on W. Okay. So that introduces, I would say, a little bit of problem. Okay. Because if M does not halt on W, then this N will have to take a decision. That type of reduction is already not covered in the previous example. If M halts, then take some decision. And now M will have to, rather N will have to take the decision if M does not halt. Okay. So, but still in this case, it's not so difficult. First of all, completely ignored its own input V. Run M on W, simulate M on W. Okay. After writing W to the tape, because it is in the finite control. And simulate M always means after doing this erasing and writing W on the tape, switch to the start state of M and then keep on happily simulating this. And if M accepts, what should you do? Accept. So if the simulation halts, then L of N should be infinite. So simply accept V, whatever it has. If the simulation halts, just accept V. Okay, so in this case, taking the decision is not so difficult. Okay, so let us see. If M does not halt on W, then this simulation will never end. Simulation on the second line. Therefore, N will never come out of this loop and will accept V. In particular, the language of N will be empty. It accepts nothing because it keeps on simulating M on W forever. And that empty set is basically a finite language. It's of size 0. On the other hand, if M halts on W, then this machine will always come here and accept its own input V, whatever it is. It does not remember it, okay, but it accepts V. So in this case, the language of N will be the entire of sigma star, and which is definitely infinite, whatever sigma is. Countably infinite, but it doesn't matter. It's infinite after all. Okay? So that was our basic goal. This new machine N is going to accept a finite language if M does not halt on W. And if and this new machine N is going to accept an infinite language. If it is not that, M does not halt on W, that is if M halts on W. And this objective is satisfied by this reduction. Okay. Yeah, so for all reduction examples, you know that your reduction algorithm is just converting the instance of one problem to another problem. You are not solving neither the source problem nor the target problem. So n doesn't have to run. It is sufficient that this reduction algorithm produces a description of n. And the description means its behavior on its own private input. Okay. So you never actually try to solve M1W or whatever problem n is. Okay. Okay. So this is just a cautionary note, and that completes the reduction. The second one is actually very, very tricky. Okay, so what does it say? I will make a reduction from HP complement to fin complement. So earlier, what I have done, I have the luxury of happily simulating M1W forever. And in the process, I also never accept anything. But now the situation is different. Again, the input is M and W, and I want to build a Turing machine N such that, because this is a reduction algorithm, the language of N will be infinite if and only if M does not halt on W. That looks like a complicated thing. Okay. The earlier reduction will simply keep on simulating M forever, accept nothing. What I do in this case, if M does not halt on W, then N should accept infinitely many strings. Okay. So this reduction is going to be somewhat different and very, very tricky. Yeah. Yes, yes, we will do something like that. Yes, yes. Yeah, we will do something like that. And in any case, to start with, it seems pretty, difficult, right? If M does not halt on W, the simulation will never halt. So how can I accept infinitely many strings? Okay. This essentially means that I will not continue the simulation forever. I will make a limited time simulation and see if it has halted. That simulation of M on W in limited time has halted. Then I will take a decision. Otherwise, I take a limited decision, other decision. Okay. So the idea here to solve the problem is to make a limited time simulation. And what should be that limited time? It may be the length of V. Okay. V is an independent input for N. Okay. And by limited time means it should not be like run it for 100 steps, a constant number of things. Then you will see that this will not be a proper reduction, because the simulation of AM on W may halt, but after 100 steps, maybe in 1,000 steps. So we'll make the limited time run only for 100. It actually may not be able to capture the halting or non-halting pattern of M on W. Okay. So it should be a parameter of something. And that only thing that we have in our hand is the length of V. Okay. So what this N does, store V on a separate tape or track, whatever, and write W on the first tape or whatever, simulate M on W, not forever, but for as many steps as there are symbols in the input V. How can it do it? So it's possible that this V is actually stored in a separate tape, okay, which may have it head as stationary. So one by one, it will simulate one step of M on W. And after simulating one step, it will just move that second step head one step forward. Okay. So at most, this many steps. So this is doable, right? And then accept if the simulation does not halt in these many steps, otherwise reject. Okay. In fact, you see that this machine is going to be a total Turing machine, because after finite number of steps, it is taking a decision, accept or reject. Okay. But then let us see that our objective of designing a proper reduction map is fulfilled with this algorithm. Okay, except if the simulation does not halt in these many steps, otherwise reject. Okay. And you see that if M does not halt on W, and it does not halt in any finite number of steps, 100, 1000, million, 2 power billion, whatever it is, the limited time simulation will never halt, because M actually does not halt. Therefore, this condition is always satisfied if the simulation does not halt in these many steps. This is always satisfied irrespective of the input, and it will accept. And will accept. In other words, if M does not halt on W, it does not halt in any finite number of steps like the input length. Okay. So, well, if N is going to accept everything. In particular, its language will be sigma star, okay, which is infinite. Okay, so that is one direction. Other direction is if M does halt on W, then you see that the language of N will not be empty. If M halts on W in some number of steps, maybe S steps or something like that, and if the simulation runs for less than these many steps, the halting behavior of M on W cannot be detected. Okay, so let me see if I have used S. Okay, so suppose that M halts on W after S steps. Okay, and let the size of the input be N. If N is less than S, then this limited time simulation will not be able to observe the halting of M on W. Just because it did not run the simulation for sufficiently many steps. However, if N is bigger than S or bigger than or equal to S, okay, then this simulation takes sufficient time for M to reach a halting state. Okay. So in that case, what should I say? The language of N is so all strings of length less than S, which is finite. Okay, it's not empty, but it is finite. Okay. So if N is greater than or equal to S, the simulation of M on W halts within N steps, and therefore N rejects V. And if N is less than S, the simulation does not halt. So N accepts S, and therefore the language of N is nothing but Set of all strings over sigma of length less than s. And this s actually depends on m and w, but anyway, it's a finite quantity. Okay. And therefore, this is the set of all strings of length less than s. This is basically a finite language. Okay. So that's it. Yeah. So once again, I will say that this type of proofs often comes into picture. Make a limited time simulation and take a decision based upon that. Yeah. But you should I would say you make some practice. Maybe we will solve one example of this type in Thursday's tutorial. And that will eventually clarify other concepts like this. Okay. So the earlier thing was a full-time simulation. It doesn't halt. Keep on simulating. Accept non-empty. Accept the empty state. Now you make a limited time simulation, and if you fail to detect a halting pattern, do something maybe bad. Okay. And if you detect, do something good. So you are doing something bad only when the limited time simulation did not run that long. Okay, and that's the idea. Okay. Okay, so that's about this. So maybe we will solve one or two exercises from this set.
Sir, I have a question.
Yeah, tell.
So, could we have done something like this? Let M, if we run time sharingly, like we run the W on M until it halts, and in each step we accept one separate string, like some other string. For in the first step, let's say we accept 0 epsilon, then 0 1, then 0 0 1 0 1, as like sigma star is countable infinite. Can we do that?
Uh, Actually, this your voice is resonating too much. Would you do one
Uh,
thing? Would you write your query in the chat so that I
okay,
can
sir.
read it?
Okay, sir.
What is the chat thing? No. I should come here. Okay. Yeah. We simulate M1W, and on each step, we accept a separate string from sigma star. What do you really mean? First of all, let us, you just confirm that you are talking about the last reduction. Yes or no? Okay, fine. We simulate M on W on each step. No, not on each step we are accepting things. If the input is of length S, okay, we will simulate for at most S steps. If the simulation has already halted by that time, I will reject. If I'm trying a different reduction from the same thing. Oh, I see. No. I'm trying a different reduction for the same thing. No. Look. in the target machine is given a fixed input V. Okay. So whenever this n accepts or rejects, it will always talk about this V, not other things. Okay. Yeah, the point is S is not known. S is not known beforehand, right? S may even be infinity. Yeah, then? Uh, uh, yes, yes. So you have to do it. Otherwise, how will you compare with the input? Somewhere I have to store. No, I do not understand your query. This is what we are doing, right? You have an input written somewhere. It's copied somewhere. And only the length of that input is important. So make one step of the simulation and move this thing. Then what are you considering? Okay. Okay. Value. Yeah, that is fine. You can take it as the value, or actually I am taking the size. That is fine. That is fine. That is not an issue. But it should be a function of V. It's basically the same thing, right? Okay. Exceeds the value or exceeds the length, then you immediately go and accept or reject, something like that. Okay. So whether you treat that V as a value or just a length, that doesn't really matter. That doesn't matter. Okay. So any other question? Yeah, the idea is that after some finite number of steps, you should stop. Because you cannot take a decision after an infinite simulation. So here I am using the length of n. You can use it as a value. That's fine. Okay. So, okay. Okay, so tomorrow we will see Rice's theorem, which is a very powerful theorem because it essentially implies that practically everything about Turing machines is undecidable. And some other things, not practically everything, I would say, these are also unsemi-decidable. Okay. Okay, so see you tomorrow. Okay, so let us, if you have any further question, either speak or write here, or else let us call it a day.